So the definition of the Wronskian is this function that takes in a bunch of other functions, and it's a determinant of a matrix of those functions and a bunch of their derivatives. But then what does it actually do? What is it used for? So intuitively, the meaning of the Wronskian is being able to solve for any initial value problem, meaning any initial conditions for an initial value problem. And right, so let's say you have an initial value problem. In this example, it's just y double prime plus p of x times y prime plus q of x times y equals 0. And we're given some initial conditions. Y at x naught equals y naught. X naught and y naught are numbers. And the function y prime at x naught equals y naught prime. Y naught prime is another number. Right, so this is linear. And we want to figure out, the solution to this is we're going to have two homogeneous solutions. So we're going to have y of x, the solution is some constant c1 times y1 of x plus some constant c2 times y2 of x. And so that's going to allow us to solve for the first initial condition here. To solve for the second initial condition, we have to figure out what y prime is. Well, let's just go ahead and write that down. So we're going to have y prime of x is equal to c1 y1 prime of x plus c2 y2 prime of x. Right, so now if we plug in the initial conditions, the actual values, x naught, into these two functions, we'll get y of x naught equals c1 times y1 evaluated at x naught plus c2 times y2 evaluated at x naught. And that has to equal this number y naught. And we're also going to have y prime evaluated at x naught. It's going to be c1 times y1 prime evaluated at x naught plus c2 times y2 prime evaluated at x naught, which is going to equal some other number that's been specified in our initial conditions, y naught prime. Now the thing is, we can actually write this as a matrix equation. So here we have, when we have the function y sub 1, and we evaluate it at a number, it's going to be a number. Y sub 2 evaluated at a number x naught is going to be a number. And we have y sub 1 prime evaluated at x naught is going to be a number. Y sub 2 prime evaluated at x naught is going to be a number. The things we don't know are c1 and c2. Right, two equations, two unknowns. We have c1 times a number plus c2 times a number equals a number. In the next equation, we have c1 times probably a different number plus c2 times probably a different number equals a different number. We can write this as a matrix equation. So let me just give myself enough room here. So our matrix is going to be y1 evaluated at x naught, y2 evaluated at x naught, and y1 prime evaluated at x naught, and y2 prime evaluated at x naught. And that's multiplying the unknown vector of the constants, c1 and c2, and we have to try and pick those constants to equal these other given numbers to us, y naught and y naught prime. Well, alright, so if I can pick whatever I want for y naught and y naught prime, and I can pick whatever I want for x naught, this matrix could have a bunch of different stuff in it, but I'd like to know if I'm always going to have a solution. And so, right, if you have a matrix like this, and you want to make sure there's always a solution, and there's always exactly one solution, right, so meaning I can solve every single problem, and I'm going to have only one solution possible for it. One of the conditions for that is the determinant of this matrix can't be 0. Right? So if I take the determinant, sorry, let me write that in print. If I take the determinant of y1 evaluated at x naught, y2 evaluated at x naught, y1 prime evaluated at x naught, y2 prime evaluated at x naught, well, that's going to equal y1 evaluated at x naught times y2 prime evaluated at x naught minus y1 prime, sorry, y2 prime, y1 prime, sorry, evaluated at x naught times y2 evaluated at x naught. Which is the Wronskian? It's the Wronskian, though, is more general. So the Wronskian is for any value of x. So right, I could pick any value of x naught here I want, and I want to make sure I can always solve for the right-hand side. Well then, if I do that, I'm going to kind of get, instead of a number for the determinant, the Wronskian of y1 and y2, these functions, are going to be y1 of x times y2 of x, prime, minus y1 prime of x times y2 prime of x, y2. I want this to not be 0. Want to not be 0. Because otherwise I might have a problem solving. It's going to turn out that being 0 sometimes is actually okay. You can still solve for the initial conditions, and that's going to be the theorem in the next slide.